We just continue where we left in the first part. So now we are able to come up with concentrations N for free electrons and P for free holes. Those are the equilibrium concentration of electrons in the conduction band and holes in the valence band. Now, I just told you that if we have an intrinsic semiconductor, then these concentrations N and P are equal. Each electron that goes to the conduction band leaves behind a hole in the valence band. So, that concentration number, let's call it N sub I. So N sub I is a concentration, a carrier concentration, which we call intrinsic carrier concentration. The carrier can be electron or can be hole. Intrinsic meaning it's for an intrinsic semiconductor. So this number, which I call the intrinsic carrier concentration, is equal to either the electron concentration, free electron concentration, or free hole concentration. Now what I'm going to do is I'm going to go back to the expressions for N and P in the previous slide and set them equal to one another, because in a semiconductor which is intrinsic, we know these two are equal. So what I'm going to do, if I just clean this here, what I'm about to do is to set N, okay, equals to P, okay, so that they're equal, or in this form here, N equals to P. So what do we have? We have this term, which is the same as this term, except for the effective mass of electrons here and the effective mass of holes here. So everything else will cancel out from the two terms, from the two sides of the equation. Now, after that, we're left with the exponential part and the exponential part here. Again, in the exponential part, we have EF, we have KBT, and we have here KBT. But when we look at the two sides, we probably divide this exponential by this exponential or vice versa. And in that case, we are going to subtract the exponents. Or if we use this form here and this form, then we have NC and NV appearing on both sides of the equation, as well as the exponentials. So after setting them equal and reorganizing, if I use the form of NC and NV, you can reorganize the terms. So in other words, if we use this combination here, okay, we can reorganize the terms, and you can immediately see that EC plus EV over 2 plus KBT over 2 log to power base E, NV over NC is equal to EI. Okay, so EF, this constant, which we call the Fermi level, it turns out to be equal to EC plus EV, that is the two edges of the conduction and valence band added over 2, and then times this factor. This factor has the logarithm of NV over NC, and then a temperature dependent prefactor here. If you use this form together with this form, as I told you, you have M star N and M star P, and you could still write the Fermi level here as EC plus EV over 2, and then the factor, the pre-logarithm factor, transforms a little bit, and you get M star P over M star N. That's the Fermi level, EF, which is that constant in the occupation probability. Now, that constant has some significance, okay? It's even a constant in occupation probability, but it now will have a meaning in the semiconductor because it's edge of the conduction band, edge of the valence band, divided by 2. So let us draw a diagram like this. This is my EC, and this is my EV. And let's assume that my 0 in energy is here. So this distance is EV, okay? And this distance here is EC, okay? So if I add the two, EC plus EV over 2, what I end up getting is a point here, which is exactly in the middle of the band gap. If you add these two and divide them by 2, then you exactly get the middle point of the band gap. Okay? So this first term, so this is EC, this is here over 2, this is EC plus EV over 2 in the middle of the band gap. Okay, so the first term of this equation for the Fermi level is actually the middle of the forbidden gap, plus this term now, or even better here, if you look at it this term, this is the middle of the band gap, plus this term. Now, let's assume that the effective mass of the electron or hole is equal to the effective mass of the electron. So let's assume that this is roughly equal to 1. And the logarithm of 1 is 0. So that means this term is very close to 0. Okay? So actually the Fermi level in an intrinsic semiconductor is very close to the middle of the band gap. So to make things nicer, okay, one can say that in an intrinsic semiconductor, okay, where you have your EC here, that's your conduction band, up here, that's the conduction band, okay, and this is your E. This is your valence band, and this is your EG, okay, which is your band gap. The Fermi level for this intrinsic semiconductor, EF, which I'm going to call EI, special Fermi level EI, I for intrinsic. So the Fermi level in an intrinsic semiconductor is around the middle of the band gap. Okay? So it's a statistical parameter. It tells us that all states below the Fermi level are occupied, all states above the Fermi level are empty. That's the case at very small temperature. So the Fermi level in all approximations for an intrinsic semiconductor is near the middle of the band gap, okay? And it is slightly away from the band gap by a very small factor, which is this one here. So for a Fermi level, that's exactly what I said. The second term is very small, so the Fermi level is in the middle of the band gap. That's one thing. The other thing is, instead of setting, since n is equal to p, let's multiply them now and see what we get. Remember, n is equal to p, and each one of them is equal to what I called Ni, which is the intrinsic carrier concentration. So if I multiply them, I get Ni squared. And let's see what you get if you multiply these two here. If you multiply, again we clean, Okay. So if we clean, and let's say if we multiply this one and this one, okay, we get NP, which is Ni squared. So we get Nc times Nv times exponential. So you have to add these two exponents. This one, you add it to this one. Okay, that's for multiplication. And so what you end up getting is you get EC minus EV. And if you look here, right, in this, I don't know, maybe I had a diagram here, EC minus EV is your band gap, right? EC minus EV is this difference here, which is EG, okay, which is here. So the intrinsic carrier concentration, which is equal to the electron concentration or hole concentration, is the square root, and it's given by this expression. It is the square root of Nc times Nv times exponential minus Eg over 2 kBt, where Eg is the difference between the bottom of the conduction band and the top of the valence band. At room temperature for silicon, we know, so what we can do from here is we can calculate Nc for silicon, Nv for silicon at room temperature. At room temperature, we have T equals 300. We know for silicon the band gap is 1.12 electron volts. So if we substitute for room temperature, we immediately see that the free carrier concentration, Ni, is equal to 1.45 times 10 to 10 per cubic centimeter. In gallium arsenide, we find it equal to this, 1.79 times 10 to 6 per cubic centimeter. So these are the free carrier concentrations, which is the concentration of free electrons and the concentration of free holes in an intrinsic semiconductor. Now I'm going to do a problem, just to try to cement this or to try to understand this. Let us have a compound semiconductor, which is gallium arsenide. We know from the tables that I showed you the band gap for gallium arsenide is 1.42 electron volts. A conduction band effective density of states for gallium arsenide at 300 Kelvin is given by this number here, 4.7 times 10 to 17 per cubic centimeter. Remember, it's a density of states per cubic centimeter. And the valence band effective density of states, NV, which is 7 times 10 to 18 per cubic centimeter, again at room temperature, which is 300 Kelvin. Now the first question is, compute the whole concentration P at 300 Kelvin if the material is intrinsic. So let's do this. This is the expression we just got for the free carrier concentration in an intrinsic semiconductor. It's the square root of Nc times Nv times exponential the band gap over 2 kb times T. So let's substitute. We're told that Nv is 4.7 times 10 to 18. Here it is, per cubic centimeter. We're told that Nc, that's Nc, sorry, Nc is 4.7 times 10 to 17. Sorry. We are told that Nv is 7 times 10 to 18. So instead of Nv, we're putting 7 times 10 to 18 per cubic centimeter. We're told that the band gap is 1.42 electron volts. So here it's 1.42 electron volts times 2. This is Boltzmann constant. It's 8 point, so kb, which is Boltzmann constant, is 8.6 times 10 to minus 5 electron volt per Kelvin, degree Kelvin. Okay, so immediately we can substitute that. Why did we choose that? Because this is here in electron volts, and so we have to choose. This is always in energy per temperature, so we have to choose it in electron volts per Kelvin, so that electron volts cancel out with electron volts, and this over Kelvin canceled out with Kelvin here, and so you get dimensionless or unitless exponent, as we should expect. So we substitute for T, 300 Kelvin, and what we get is Ni for this gallium arsenide, 2.16 times 10 to 6 per cubic centimeter. This is the concentration of free holes and the concentration of free electrons that are equal in a gallium arsenide intrinsic semiconductor. I think we said it here. We said in gallium arsenide we get something like 1.79 times 10 to 6 for Ni. So we got something here very close, right? About 20% close. So this is Ni of gallium arsenide by calculation. Then the second question is, determine the Fermi level EF in the gap of this intrinsic gallium arsenide material at 300. So what we're going to use, so this is my P now, that's a concentration, because P is the same as Ni, and N is the same as Ni, so each one is the same, so P is 2.16 times 10 to 6 per cubic centimeter. This is the concentration of holes in my gallium arsenide. Now the Fermi level can be obtained from that equation, right? But I'm going to put EC plus EV over 2 as the middle of the band gap, EG over 2, call it. So my equation becomes EF, that's the position of the Fermi level, is the middle of the gap, plus this factor here. So I'm going to substitute kV in electron volts per Kelvin, 300 Kelvin for temperature. And then this is my NV for gallium arsenide per cubic centimeter. This is my NC. And then if I do all this, I get EF equals 0.74. Remember, gallium arsenide has a band gap we're given of, in the problem, we're given that the band gap is 1.42. So this is 1.42. And what we're getting is, where is the Fermi level? The Fermi level is 1.42 times this factor, so it's 0.74. So mid gap is something like 0.71. That is the middle. That's when you divide 1.42 over 2, you get this one. This is EG over 2. Okay. And what we're getting for the Fermi level is just slightly above here, which is 0.74. Okay. So, in other words, it's very close to the middle of the band gap. And this is what we expect for an intrinsic semiconductor. And then the next question is, compute the electron concentration N at 400 Kelvin in gallium arsenide if the material is still intrinsic. Now, remember one thing. For a material that's intrinsic, P is equal to N. Each one of them is equal to Ni. And we got at 300 Kelvin 2.16 times 10 to 6 per cubic centimeter, right? That is the concentration Ni that we get. Okay? And this Ni is equal to both N, concentration of N, and concentration of P. That is at 300 Kelvin. Now, the question that we're asked is to find this concentration at 400 Kelvin. So, essentially, we should go back put NC, NV, EG, but now we use T equals 300. But what we have is NV and NC at 300 Kelvin. So we have to go back and use the expressions for NC and NV and see if we can produce NV and NC at 400. So what we're getting here is we know expressions for NC, and NC is proportional to the temperature to 3/2, right? Because if you look back, go and look back, that's what you'll find. And NV is proportional to the temperature T to 3/2, right? So the difference, so NC and NV are proportional to this temperature, and I got this from expressions here. If you go back all the way, look, this is NC, and you can see that this is the temperature to power 3/2, and this is your MV here, and this is the temperature to power 3/2. So NC is proportional to T to power 3/2, and NV is proportional to T to power 3/2. And that's what I wrote here, right? Okay, so if we know NC at 300, we are given that, we can get NC at 400 by simply multiplying by 400 over 300 to power 3/2. So we use the same NC that we've gotten for 300 and multiplied by this factor, 400 over 300 to 3/2. So we get for NC at 400, we get this value, higher value. And for NV at 400, we do the same. We get this value, 1.08 times 10 to 19. And now these are the NC and NV that we need to use in NI. So now you see here, this is your NC at 400. This is your NC at NV at 400. This is your energy gap, EG, which is the same. This is your KB, which is Boltzmann constant, the same. This is your temperature, which is 400. Now, what do you get? You get 2.8 times 10 to 9. You see, if you increase the temperature by 100, now you get more free carriers, more free electrons, and more free holes. So that is your Ni. Remember, Ni at 300 Kelvin, that was much smaller, right? If we got at 300 Kelvin, we got Ni equals to 2.16, right? Times 10 to 6. So we have almost 3 orders of magnitude difference, okay, between Ni at 400 Kelvin and Ni at 300 Kelvin. So this is the concentration of free electrons, and also it's the concentration of free holes in the intrinsic semiconductor at 400 Kelvin. So this is, why do we bother to find the density of free electrons and free holes in a semiconductor? Because these are the electrons and holes that are responsible for current transport, for current in the semiconductor, and therefore for current in the devices, which we will look at immediately after that. So what I will do is I will stop here.